This is the first in a series of resources on limits. We consider the basic idea of a limit and provide a formal mathematical definition for a limit. We look at 3 instances where a limit does not exist. We explore various properties that make finding limits simpler and look at multiple examples. We consider what it means for a function to be continuous as it pertains to limits. We close this series by considering infinite limits. What comes to mind when we think about the word limit? Maybe you think of a physical limit, like a workout goal, or a personal best effort. Or maybe you think of a weight limit on an elevator. Mathematically, a limit has a more specific definition. In math, a limit means we want to see what happens to a function as we get closer and closer to a given value for the input. The notation that we will use is LIM over x with a right arrow at a value c, and then write whatever is the function. We read this as, quote, the limit as x approaches c of f of x. One of the easiest ways to determine a limit is to look at the graph of the function. Let's take a look at a couple of examples. Suppose we want to find the limit as x approaches 3 of the function x. When we look at the graph of this function, we see a nice straight line. It becomes obvious that the closer we move to x equals 3, the closer our function value also gets to 3. So the limit as x approaches 3 of the function x is 3. Let's look at one more example. What if we want to find the limit as x approaches 2 of x squared? Looking at the graph of the function, we see the nice traditional parabola. As we get closer and closer to x equals 2, we approach a y value of 4. So the limit as x approaches 2 of x squared is 4. But does it matter how we approach our x value? It turns out that how we approach does indeed matter. There are different notations to imply approaching from the left or right. A limit written as limit as x approaches c with a plus means that we approach from the right, or the positive side, moving to the left toward the value c. A limit written as limit as x approaches c with a minus sign means that we approach from the left, or the negative side, moving to the right toward the value c. In order for the limit to exist, the limit from the right must exactly equal the limit from the left. Let's see an example. Suppose we consider the function graphed, and we want to find the limit as x approaches 2 from the right, and compare that with the limit as x approaches 2 from the left. As we approach and get close to 2 from the right, we get closer and closer to 2. When we approach from the left, however, we close in on a different value. The limit as x approaches 2 from the left is 3. These piecewise functions lead to a couple of additional interesting situations, as we shall see. A function does not have to be defined at an x value for the limit to exist at that point. For example, consider the function x squared minus 1 divided by x plus 1. We want to find the limit as x approaches negative 1 for this function. Take a look at the graph for this function. It looks very much like a straight line, except there is a hole in the graph. This hole is exactly at the x value of negative 1. So our function is not defined at the point we are concerned with. However, when we look at the graph, the y values approach negative 2 as we get close to x equals negative 1. So the limit as x approaches -1 for x squared minus 1 divided by x plus 1 is -2. It is also possible for a limit to equal something other than a function value at a point. Consider the graph shown. We want to find the limit as x approaches 1 for this function. The function value for x equals 1 is 3, as depicted by the single point. However, the remainder of the function follows the graph of the line. If we approach x equals 1 from the right, we have a limit of 1. As we approach x equal 1 from the left, again we have a limit of 1. So even though the function actually equals 3 at x equals 1, the limit as x approaches 1 for the function is 1. Now that we have explored the general idea of the mathematical definition for a limit, let's discuss the formal definition. We discussed the idea of getting close to a value and that a function value is close to some value. What exactly do these terms mean mathematically? Suppose we have some function f of x, and that the limit as x approaches c is equal to some value L. We create the formal delta epsilon definition for a function limit as follows. If we have some small value epsilon, there exists a value delta such that if the absolute value of the difference of x and c is between 0 and delta, then the absolute value of the difference between f of x and L is somewhere between 0 and epsilon. This means as we get close to the limit L, we can find an x value that provides that function value. We will use this formal definition in the next resource in the series to explain certain limits that do not exist. Stay tuned.